work at Glenunga International High School here in Adelaide, Australia. We're a public IB school with a cohort of around 200 students, and they represent 85 different cultures from around the world. The school is set in the eastern suburbs of Adelaide, where we're close to the hills with beautiful nature, wineries and wildlife. I like living in Adelaide very much. The weather is always nice and hardly ever rains. If you want to buy an ice cream and you are U1, which is the closest ice cream stand that you could go to? The first activity is about Voronoi diagrams, and we want students to understand how Voronoi diagrams are constructed. And I want you to look at the animation, and then I'll set a timer and give you 1.5 minutes in your group to discuss what you see happening here mathematically. How is it mathematically figured out which is closest? So here's our animation. So we have a scenario with ice cream stands in the park where we have a look at which ice cream stand is closest.
It's expanding at the same time,
Yeah.
but because we're determining like which one is closer, there's obviously going to be a difference in distance.
But then does that necessarily mean that there's a shorter distance between them? Because it's going faster, it's gonna reach there faster.
Yeah.
Oh, yeah.
Yeah.
So we can't determine the radius then.
Yeah. So it has to be at the same rate if you want to know which one's closer.
And it turns out that the perpendicular bisector is the mathematical way to establish the boundary line between those ice cream stands. Then we complicate things by introducing more and more points. So a third point, a third ice cream stand, would create additional Voronoi edges. And those Voronoi edges, they come together in one single point that is equidistant to all three of the ice cream stands. So if you open up the tools and choose the circle tool, you can start a circle with the center J. And see what happens.
So does that mean that they're all equal distance?
Yeah, because it's the radius of the circle. It should all equal.
Yeah.
The distance is the radius of the circle. So by using the technology, we have the option to explore various pathways to the solution, and the students, they can find what they think is the best pathway.
By using this technology, it was more insightful in a sense, because when you're working this question out by hand, obviously, it's all, numbers and calculations, and you don't really understand how this can be replicated visually.
We can graph a very complex function on the technology, and you can do it by hand. So it's so much easier, and also you can visualize things because you can actually see the graph.
In the Voronoi exercise, we can see how it helps the students to explore that problem rather than just find the answer to something.
Because all of them, the radius is going to be the same for 3 different points. So if we make a circle and see which radius has the biggest circle, then we know that that point is the furthest away from all the other parts.
So in the next task, we'll look further into modeling. And this task is set in context of a game reserve where an elephant has been found, and that elephant has been the victim of poachers. And we're trying to model our way to the time that the crime was committed. That point, -3.167, is indeed a negative time. What can we tell from that negative time?
The temperature of 36.5 degrees was about just over 3 hours ago.
How does this model fit the real-life situation?
The drop of temperature slows down as it gets close to the environmental temperature.
Yeah. And this model will show that, right?
Yeah.
And if you would bring up, maybe with the older data, the polynomial model, is it a mathematical good fit?
Mathematically fit,
Yes.
but it doesn't fit the real life situation.
Yeah.
Perfect mathematical fit doesn't fit the real-life situation, though, because that elephant seems to come alive somehow.
Yeah.
If you do an activity like this with paper and pen, I don't think it would be as enjoyable in the first place, whereas the technology that we have now with the laptops and the software can really help us understand the problem and make it visible and help us to view different approaches to that problem, as well as getting the answer for us. So you can actually do inquiry-based learning with it. With the technology available today, we really need to encourage students and teachers to use it, because it's really the way forward with teaching mathematics. Why would you do it with pen and paper when you can do it with all these beautiful tools that we have that go 3D, that go artificial intelligence, augmented reality? I'm really excited about the future of maths and technology in mathematics and how it will change our classrooms in the future.